So we've got secant squared theta. What do I need to put with it? D theta dt equals, do I have to use the quotient rule there? It is like 1 over 2,000 times s. So I don't have to use quotient rule. You can, but you don't have to, and it's going to be easier if you do not. So the derivative of 1 over 2,000 s is just 1 over 2,000 ds dt. All right, so now, the derivative itself is not really all that bad. What's difficult about these problems is sometimes coming up with the equation you need to use and then searching and finding all the pieces that you need. So what information do we have that we could plug in? Do we have theta? Do we have d theta dt? No, in fact, what are we looking for? We're looking for d theta dt because it's asking find the rate of change in the angle. That is your d theta dt. So this right here, the d theta dt, that's what we're looking for. So we're not going to replace it. So we don't need to try to find it. But we're going to need theta. Do we have ds dt? Well, we need 50t squared. That's what we're going to use. But what does s stand for there? S stands for this length, right? So this is not ds dt. It is s. But I could take the derivative there. So for this ds dt, I could do s equals 50t squared. I could take the derivative of this, ds dt, with respect to t, equals, I will get 100t. Do I need a dt here? I do not, because I'm taking the derivative with respect to the t. Right, t is our time. So I don't have to put that there. So I've got ds dt, and I know t is 10 seconds, so that's going to be 100. So ds dt is going at t equals 10 is going to be 100 times 10, which will give me 1,000. So I got ds dt, that's 1,000. So I've got secant squared of something here, d theta dt equals 1 over 2,000 times 1,000. Right here. This is ds dt, and I've got the line such that t equals 10. That's just showing you're plugging in 10. All right, we've got ds dt. What else do we need? We need the angle. How are we going to find the angle? We're going to need some trig. If I knew this side, I know the bottom side is 2,000. That's not changing. If I knew this side, I could find the angle at that point. How could I find this side? Plug into 50t squared. So s equals 50 times 10 squared. And so S is going to be 50 times 100. So S equals 5,000. So this side right here is 5,000, but S is not what we need. We need theta. So what could we do to find theta? Tangent. So tangent of theta would equal 5,000 over 2,000. So tangent of theta is 5 halves. We are going, how do we get rid of tangent? Inverse tangent. And we are going to do this in radians because everything on the AP exam is in radians, but if you put your calculator in degree mode, it'll give you degrees, and then your answer will be in degrees, but we'll do radians just because. Now, our book is not so exclusively radian-ish, so I can't even remember particularly here which one the book uses radians. I think it uses radians, but sometimes our book might use degrees. So if you notice your answer's not matching up, check your units to see. So if we do inverse tangent of 5 halves, we get 1.19029. And so that is our angle. Remember, that's in radians. So it doesn't seem right because it doesn't seem like it should be 1 degree, but it's not. It's radians, so that would be better. So then we've got everything plugged in. We need to solve for this. So in my calculator, how do I do secant squared of that number right there? You might be able to do secant. Can you do secant? Maybe. Let's see. Yeah, you can do, if you go to catalog, it will do secant. So you could do secant of this number. And you want to hit enter first and then square that. So you get 7.25. 7.25 d theta dt equals 1/2, and you would divide both sides by 7.25. And 0.5 divided by 7.25 is going to give us 0.06896. And this is radians per second. So at 10 seconds, the camera should be changing at 0.06896 radians per second. There. If you forget how to get to secant on your calculator, you can always do it this way. Secant is 1 over cosine, so you could do 1 over cosine of the 1 point whatever we had there. You can do that, which gives you this, and then square it without having to go to any special menus if you don't want to go to the special menu or forget how to. So if this was something that was going to be difficult to catch, you could program using this so that your camera would like automatically do that if it was something really quick where you weren't going to be able to do it by hand. The closer you are to the base of the rocket, of course you're just going to see smoke if you get too close, but the closer you are to the base of the rocket, the faster it's going to be at first. All right. I always forget that I need to put a diagram of how an engine works here for this. So, quickly, or not a diagram, but a video. Alright. Okay, this one looks pretty short. Okay. Everybody know how a 4-stroke engine works? Some of you. If you don't, we're going to watch this video, which is hopefully decent, because I haven't previewed it. It's all famous. Jasper Mahoon knows. Their picture looks good.
A basic lesson in the fundamentals of a 4-stroke EFI gas engine may be helpful to your understanding of Mercury products. Here are the basic components of every 4-stroke gas engine. A piston, a connecting rod, a crankshaft. As the piston travels up and down in the cylinder, this lateral motion is turned into a rotating motion at the crankshaft. The longer the stroke of the piston, the larger the displacement of gas and air occurs in the cylinder. To propel that piston, we need to ignite a tiny bit of gas and a whole lot of air. This creates expansion inside the cylinder. The fuel delivery system consists of an air intake manifold, valves,
telling me more than I want to
intake and exhaust.
Oh, here's what I want. I want you to see the
stroke because a 4-stroke engine is called a 4-stroke because 4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke. The fourth stroke is the exhaust stroke. As the piston travels upward, the exhaust valve opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again. It takes one up and down motion, or 2 strokes of the piston, to create 1 revolution of the crankshaft. RPMs, or revolutions per minute, is how many times the crankshaft rotates within that minute. At wide open throttle, the crankshaft may turn at 5,000 RPMs, or a dizzyingly 83 times per second. Meanwhile, the piston traveled up and down 166 times in that same second. Want to see how fast that is? Now, that's fast. Let's see it again. Amazingly, the 4-stroke EFI engine does this smoothly, quietly, and reliably for years and years of operation.
It is pretty crazy to think about.
Anything slightly messes up your entire engine.
Yeah. And you can see why, because it is amazing that we can make something that will work for that long.
With explosions.
That fast, with explosions at high temperatures. It's pretty crazy. This is basic technology. This is stuff they figured out long ago. Well, I mean, I guess, yeah. This is crazy. This is a pretty good video. This is one of the better ones I've watched. I need to put the link here. Put that in my notes.
none of that knowledge, how do you even think I'm going to make tiny explosions on this little rotating stick that's going to happen at opposite times to balance this engine that's going to move wheels?
Yeah.
Money.
I mean, yeah, but you gotta think about, like, the first person to figure all that stuff out is pretty crazy. Like, I can understand how it works. I can't personally recreate it, but maybe with the knowledge, I could recreate it. Probably not, but I could see how one could recreate it. But to be able to do that, just be like, you know what? This might work. Let's try it.
How could you ever think that would work long term?
Yeah, and then to be able to do it effectively so that a car can run for, I mean, just think about how many rotations, 5,000 rotations per minute. And think of how many minutes you drive your car just daily. Then over, like, the lifetime of the car, and the fact that it just doesn't fall apart after a week is pretty crazy. And cars keep getting a little better, I think. They will run longer, more or less. Although transmission in my husband's truck is not proven to be very reliable. Thank you, Chevrolet. I think we're getting a new one of those soon. That's going to be a fun purchase, or he's going to want to sell it and get a new truck, which will be even more expensive than transmission. So we'll see about that. But anyway, I think it's so cool. Certainly, if you're just like a mechanic working on cars, you're not going to be doing calculus to analyze something here. But certainly at like a design sort of level, you might look at something such as this. Obviously, I barely know how a 4-stroke combustion engine works and need a video to help explain it to you. So, I'm not saying I know how to design motors of cars, but there are people out there that do, and they probably have really cool jobs and do really cool stuff. Let's look at just like one boiled down problem here. So, this is a diagram of what we just saw there. So, we have, I've already forgot. This part's the crankshaft, right? And this is the connecting rod. So, crankshaft, have I got that right? And this side right here is connecting rod. Right, these are pieces of metal that are not going to change. If they do change, your engine's probably going to blow up. So the crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute, which we just said, obviously this is some sort of different, this is not a motor running at full capacity here because it can go like 5,000 rotations per minute. But for whatever reason, this one's moving slowly at 200 revolutions per minute. We want to find the velocity of the piston when theta equals pi over 3. So in this diagram, theta is this angle right here. What is the velocity of the piston? The piston is this thing. Well, I think that's actually maybe space. Or maybe not. No, this is space. It's this. That's this thing. So we want to know how fast that is moving. Remember, that is going just like back and forth and back and forth and back and forth. Right? So, what variable-wise is the velocity of the piston going to be? What? They didn't name it P on this diagram. We could if we were making it from scratch. But on this diagram, it's going to be X. So this is dx dt. That's what they're asking us for. Now, 3 and 7 don't change, which is good. So we can just put those into the equation as 3 and 7. What equation do I need to use? Is that a right triangle? It's not a right triangle. So can I use Pythagorean theorem? No. Sadly, I cannot. We are going to have to use trig, but I can't use just like straight sine, cosine, and tangent, because that also requires a right angle. What trig can we use that does not require a right angle? Law of sines or cosines, right? Which one could we set up here? We don't know. We're missing two things, so we can't like find a single answer. But I've got all three sides are labeled, and I have an angle. So law of cosines is going to work best here, because law of sines would leave something out. We wouldn't be able to put 3 and 7 and x and theta. We wouldn't be able to include everything if we use law of sines. Law of sines would be like sine theta over 7 equals, we'd have to think of another angle there. So law of cosines is what you want to use. This is your angle. So the law of cosines, let me remind you, is a squared equals b squared plus c squared minus 2bc cosine capital A. Where in your diagram, like you have a capital A, B, C, side A is across from angle A, side B is across from angle B, and side C is across from angle C. So since the only angle that like we're concerned with here is this angle, then that 7 right there needs to be our A. 3 and x, it doesn't matter which one's B and which one's C. So 3 squared plus x squared minus 2 times 3 times x cosine of theta. All right. Okay, we okay here? All right, let's clean this up a little bit before we try to take a derivative. So we'd have 49 equals 9 plus x squared minus 6x cosine of theta. And I'm going to even subtract that 9, so we got 40 equals 9. I'm sorry, 9's gone. 40 equals x squared minus 6x cosine theta. You don't have to clean it up, but you can. You cannot before you take the derivative, because that angle is changing. Okay, so that theta as the crankshaft rotates is going to be changing. So we cannot replace it. We also, if we use the information for pi over 3, we could also find x, but we can't replace it either because that distance for x is changing over time. It's going to continue to change. So if a value is changing as whatever happens, you cannot replace it till after you take the derivative. So after we take the derivative, we are going to replace the theta with the pi over 3, but we can't do it before. It's okay to plug in 3 and 7 before we take the derivative, because 3 and 7 are solid pieces of metal that are not changing their length. So we can, if it's something is constant, you can plug it in before. Does that make sense? All right, so let's take our derivative. Derivative 40 is 0. Here we'll get 2x dx dt. Oh my, what have we got to do here? 6x cosine theta. Product rule. So 6x The derivative of cosine is negative sine. So that's going to make that negative sine theta d theta dt plus cosine theta times 6. And then we'll put a dx dt. Okay, so we've got a theta we can plug in because they told us theta is pi over 3. So that's good. We've got the thetas to plug in there. We need an x. Do we have the x? We do not. But if we're considering that this angle right here is pi over 3, and this is 3, and this is 7, can we find x? We could, because we could do law of cosines here. So we could do 7 squared equals 3 squared plus x squared minus 3 times 3 times x times cosine of pi over 3, and that's 49 equals 9 plus x squared minus 3x times, this is cosine of pi over 3. It's 1/2, right? Yeah, 1/2. So that's going to be 1.5 x. And so that gives us a quadratic. 0 equals x squared minus 1.5 x minus 40. If we move that 49 over here. And I don't want to factor something with a fraction or a decimal in it, so let's just use our calculator to solve. 0 equals x squared minus 1.5 x minus 40. Oh, I didn't put the comma x on the end. And we get 7.1187 or negative 5.6187. And here the 7 is what we want to use. The negative wouldn't make sense for the particular problem there. So 7.11887. Alright, so we got x. What were we looking for again? We're looking for dx dt. We don't want to replace it. We need d theta dt. Do we have it? We sort of have it. That crankshaft is rotating at a rate of 200 revolutions per minute. That is almost what we need, but we're measuring our theta in radians, so we don't want to use revolutions per minute because that's a full circle all the way around. And we want to know the radians per minute, right, to talk about d theta dt. So how could I change that so it would be radians per minute? How much is 1 revolution in radians? 2 pi, right? All the way around the unit circle one time is 2 pi. So 1 revolution would be 2 pi per minute. And we got 200 of those. So what is 200 revolutions per minute? What does it equal in radians per minute? 400 pi. Okay, so now we have everything we need. So we got 0 equals 2 times 7.11887 dx dt. That's what we're trying to find. I'm going to distribute this negative here, so that'll be a plus 6 times 7.11887 sine of pi over 3. D theta dt, we said was 400 pi. And then, if I'm distributing this negative, that's going to be a minus 6 cosine of pi over 3 dx dt. This one's probably one of the longest ones we're going to do as far as setup and solving goes here. So, if we grab our calculator, if we take that 7.11887, multiply it by 2, we're at 14 point, calculator over here, so 2377 dx dt plus 6 times 7.11887 sine of pi over 3 times 400 pi. That gives us this number, 46483.9 minus 6. Cosine of pi over 3 is 1/2, so that's going to be 3 dx dt. All this equals 0. So I'm going to move this over to the other side and combine the other things. So I've got negative 16483.9 equals, that's going to be 11.2377 dx dt. Divide 2377. And I'll do negative 16483.9 divided by 11.2377. Then I will get negative 1,466.84 equal to my dx dt. And what were we even measuring? 3 inches and 7 inches. So since x is this length right here, it would also be measured in inches. So that would be in inches per minute. Does it make sense that it would be negative at that point? Where right here. Oh, that one. Yes. Oh, yeah, you're right. I did that wrong. That should be a 4 instead of. So let's go back and fix that. Which makes that change 46483.9. No, the wrong number. The wrong number down again. 4,136.42. Even bigger number. Does it make sense that it'd be negative at this point right here. We're talking about X. So if we're at this point right here, that crankshaft rotates counterclockwise. So at this point, you would have a negative because your piston would be going back. This direction would make that X shorter. But then it'll, once it gets past halfway, it's going to go back to being a positive value. But at pi over 3, it would be a negative value. So, if you needed to know that information, there it would be if you were designing something. I'm not at that pay grade to know exactly what this would be used for, but I imagine somebody somewhere could use something of this sort for something at a very high level. At a very high level. All right. Questions? That one's pretty tough. If you don't have a right triangle, you're probably going to have to use law of cosines. Okay, we really need to do a cone problem, so I hope we can get through this one. We'll try really hard. All right, a conical tank with a height of 10 feet and a diameter of 8 pi feet is being drained at a rate of 3 cubic feet per second. At what rate is the height of the water in the tank changing? So we kind of looked at one of these problems, but just at the very beginning before we were actually solving them, right? And we said as you drain the tank, if it's a cone shape, the height of the water is not going to change at a constant rate, right? It's going to be slow at first and then go really fast. I was thinking about this morning with my coffee filter because it's like a cone shape, and it, like I'm making like half of what my coffee maker will make, but it looks like coffee grounds are about to top out, but it's because that top part is so much bigger, right? So there's more room than it seems there. But I was thinking about this today. You could make a coffee filter, those cone coffee filters, and you could make a problem for this. And you got a rate in and a rate out. Oh, we could make a good problem about that. I wonder if there's any calculus in the design of those. I don't know. Well, I don't think it'll apply to Mountain Dew, but anyway, let's do the problem because I need to. So we got a cone, and be careful when they give you this. Diameter is 8 pi, but what do you really need for the? You really need radius, so that would be 4 pi, and height is 10 feet. But this tank is being drained. So that is the cone. We could find the volume of the cone. But what we really care about is the water level in the cone. All right. What we really care about this, it's going to have a radius right there of R and a height of H. That's what we really care about. So my volume formula for a cone is 1/3 pi R squared times height. Here's the issue with this problem. If I take the derivative of it right now, I've got 3 variables. So I'll end up with a dv dt, a dr dt, and a dh dt. But I don't have that much information. I've got right here the rate, let's see, the tank is being drained at a rate of 3 cubic feet per second. What information is that as far as variables go? That's dv dt. So we need to know dv dt is -3 cubic feet per second. All right. What's the question asking us for? What rate is the height of the water changing. So we want dH dt is what we want to find. Does it tell us anything about dr dt? We don't want to know it. We also don't have any clue what it is, right? So it would be in our best interest if we could get rid of the r. And we can. Okay? Because the water level cone right here is going to be similar to the bigger cone, right? So like we did on the first problem we did this morning, similar figures you can set up proportions for, right? So if I set up a proportion for this, the radius over the height, that would be the little cone, the water that's in the cone, should equal radius 4 pi over 10 here. Okay, that should always be true. As the water leaks out, that small cone of water is still proportional to the big cone there. So if I cross multiply this, I get 4 pi times h equals 10r. And I want to solve for r so that I can replace it. So I can divide by 10. And I get 2 pi over 5 times h equals my r. So this stuff right here is equal to r, so we can plug it in right here, which is going to be very helpful because it's going to get this equation in terms of just one variable, the variable that we care about, because we want to know when the height is changing. So we're going to have v equals 1/3 pi, and then we've got 2 pi over 5 times height squared times height. So let's deal with this. Let's clean it up a little bit before we try to take the derivative. So 1/3 times pi is going to be pi over 3. And then to square what's in this parentheses, I just need to square everything. So I'm going to get 4 pi squared over 25 times h squared. That's times h squared. And then I still have that times h over there on the end. So I have 4 pi cubed over 75 times h to the 3rd. We okay here? It looks terrible, but 4 pi 3rd over 75 is a number. We could type it into the calculator, get a decimal for it if we wanted. So it's a simple derivative. So dv dt is going to equal, we're going to multiply by 3 here, so we've got, that'll give us 12 pi cubed over 75, h squared, and dh dt. It does not drop the cube on the pi.
It won't make popcorn bread.
And so we know dv dt is -3 equals that 12 pi cubed over 75. Let's just get a decimal for it. 12 pi to the 3rd over 75. So that's 4.961. The height, they told us it's when the height is I think it is a bad question. Let's say when the height is 4 feet. So you have to have it. So 4 squared dH dt. And so if we take that number, multiply it by 4 squared, we're going to get that, negative 3, we're running out of time, sorry, 79.3761 dH dt. We're going to divide negative 3 divided by that number, and we're going to get this answer. So negative 0.037795. That is going to be feet per second or minute. Second is your dH dt. Okay. Sorry, we're rushed on that.